In this lesson, we're going to look at the law of universal gravitation. Formulated by Isaac Newton, the law of universal gravitation basically states that every mass in the universe is attracted to every other mass. So essentially, if an object has mass, it will also have an attractive force. So Newton's law of universal gravitation stated that the force is directly proportional to the product of the two masses involved in the attraction and is inversely proportional to the square of the distance between their centers. Okay, so now looking at this equation right here. F is your force of gravity, and that's just measuring your attractive force between your two masses. G, capital G, is known as the universal gravitation constant, and its value is 6.674 times 10 to the negative 11 Newton meter squared over kilogram squared. So just to give you a little bit of background about this universal constant, it was actually not measured until 71 years after Newton's death by Henry Cavendish with his Cavendish experiment. So if you're interested, look that up. It's a good read. So for our purpose, G is just a constant. It's always going to be 6.674 times 10 to the negative 11 Newton meter squared over kilogram squared. And right after this, we're just going to do a little dimensional analysis to help us remember these units. So M1 and M2 are your two masses that are you're measuring the attraction between those two masses. And R is going to be the distance between the centers of the mass. So centers of the two masses. So for an example, if you look at, if this is your M1, this is your M2, we're going to measure it from the center of M1 to the center of M2. That distance is going to be your R. So as promised, here's some dimensional analysis. We have our force of gravity, which is a force, so it's measured in newtons, and our gravitational constant, we said, was newtons meter squared over kilogram squared. We have our mass, which is kilograms. Obviously that's going to give you kilogram squared. You can see where this is going. And then R is a distance, so it's going to be measured in meters. And it's squared, so. Okay, so right away, you know you can cancel this and this, because that's just going to be kilogram squared. Your meters are going to cancel out, and you're left with newtons equal to newtons. So it works out. Now my question to you is, if there's an attractive gravitational force between two masses anywhere, why are their objects not constantly being pulled towards one another? Let's do an example to illustrate this. Okay, so this example, we're going to determine the attractive force between two people, 50 kilograms and 70 kilograms, separated by 10 meters. So first thing, I'm going to write down my givens. Okay, then I'm going to draw my diagram. Okay, so I made M1 female and M2 male because it's more romantic that way. And then the distance between them is 10 meters. Okay, so now let's use our equation. So our attractive force is going to equal G M1 M2 over R squared. So now let's plug in our values. And then working this out, we get that our attractive force is going to be 2.39 times 10 to the negative 9 newtons. So as you can see, this is an extremely small force and negligible compared to the force of friction between the two people and the force of gravity between the earth and each person. So now let's look at what might be the force of gravity between the two people from the last example and the earth. So again, we want to write down our givens, and I'm just going to add in a few more values that we probably need. Okay, so here I've given you the mass of the two people, the radius of the earth, and here it's in kilometers, I've converted it to meters, and then the mass of the earth. Okay, so here's our diagram. We have our Earth, and now I'm going to put, obviously not to scale, I'm going to put our guy right over there. At least I got him in the right continent, sort of. And now let's put her, actually, let's make them long distance. She's either in Iceland or Russia. I don't know. That's why I don't teach geography. So let's look at her case first. So we're going to measure her D value is going to be from, since she's standing on the surface of the Earth. Oh, that's not the color I wanted. We're going to measure it from the center of the Earth to where she's standing. And that's going to determine her gravitational pull, or the Earth's gravitational pull. Okay, so force of gravity for her, I'm going to call her FG1, I'm going to call her 1, and the guy's going to be 2.
Can I please do something?
What do you want to do?
Make my face.
Okay, so let's sub in our values.
I'll do it the
If you want to read the numbers, you can do it.
6.3.
No, 6.6.
6.67
times 10
times 10
to the negative 11.
to the negative 11 and all and the Z. So
It's a 2.
for our,
And so the mass of
our math of Sammy
Sammy,
and Betty.
no, just you. We're just looking at you now. So you're the girl. Is
Is
50 kilograms.
50 kilograms.
And because we're calculating the mass of Sammy to the mass of the Earth, we wanted their second mass is going to be the mass of the Earth, which is 5.97 times 10 to the 24 kilogram over, and like we said before, your distance is going to be the radius of the Earth. So that's 6.378 times 10 to the 6th meters squared. And that gives you 489.66 newtons. So now let's look at the gravitational pull between our guy and the Earth. So this is the distance that we're going to be looking at. And our formula is going to be Fg2 is equal to Gm1 times m2 over r squared, which is your distance. Okay, so subbing everything in, our G is going to be 6.67 times 10 to the negative 11 always, because it's a constant. Our mass 1 this time is going to be 70 kilograms. And then our mass 2 would be the mass of the Earth. Over, and then your distance between the radius of the Earth to the guy is going to be the radius of the Earth, which is 6.378 times 10 to the 6th meters, and that's squared. Okay, that comes out to 685.53 newtons. So if we compare the force of gravity in this case to the last case we did where the girl was lighter, so she was 20 kilograms lighter, this value is obviously greater. And we can conclude that the greater the mass, the greater the gravitational attraction or pull. The less the mass, the less force of gravity there is between the two objects. So the other factor that's going to affect your force of gravity is the distance between the two objects. So in the first case here, we have a smaller distance, so this results in a greater force of gravity. In the second case here, we have a larger distance, so our force of gravity is inversely proportional to your distance. If you recall, Newton's third law states that for every action there is an equal and opposite reaction. So we know that the Earth is pulling us towards its center, but does that mean that the Earth actually moves upwards towards us? In fact, according to Newton's third law, if the Earth is pulling you down, you're pulling the Earth up. If this is the case, then why does it appear that objects fall to the Earth? Why do we not see the Earth move upwards towards a falling object? Really, this should be happening every day. Well, the Earth is much more massive than an everyday object. So in fact, the Earth does move upwards towards us. However, the acceleration is extremely small compared to the acceleration of us towards the Earth. And that's because of our small mass relative to the Earth. Now, to prove this point, let's calculate the acceleration of person 1 and the acceleration of the Earth. So first thing is we want to write down our givens. Okay, so here we have the mass of person 1, the mass of the Earth, and this was the gravitational force that we calculated in the above example for between the Earth and person 1. So to calculate the acceleration of person 1, we are going to use Newton's second law. So your net force is equal to your mass times your acceleration. And we're going to solve for acceleration here. And that's going to give us your net force over your mass. So let's substitute our values. Newton's down. And this is going to be 50 kilograms because it's person 1 that we're looking at. And that gives you, try this on your calculator, 9.8 meters per second squared. Down. That's no coincidence. It's supposed to be the acceleration of gravity. So every person is going to have that. That's going to always going to be constant. So that ratio between force of gravity to your weight, or your mass, sorry, will be 9.8 meters per second squared. Now to calculate the acceleration of the Earth, we're going to use the same formula. So acceleration is going to be equal to force over mass. And according to Newton's law, your force of gravity is going to be the same, just opposite in direction. So it's going to be 489.66 newtons up over the mass of the Earth, which is 5.97 times 10 to the 24 kilograms. And that gives you 8.2 times 10 to the negative 23 meters per second squared up. So substantially smaller than 9.8 meters per second squared. And that has to do with the relative size of the Earth to a person in this case. So as we can see, the Earth does in fact accelerate up towards us. However, it's extremely small. Okay, that's it. Hope you took notes.